this video, we're going to talk about simplifying square roots, cube roots, oftentimes referred to as simplifying radicals. The first thing we have to be familiar with is some of our terminology. Over here to the right-hand side, it talks about the index and the radicand. The index is the little number that's tucked in near the square root symbol. It really tells us what root to take. And the number that's underneath the square root is referred to as the radicand. Now, in the two examples that are down here, all I'm asking you to do is to identify the radicand and the index. Now, the first one is a square root symbol, and it's very seldom ever written, but if there is no index written, it's assumed to be a square root, which is an index of 2. So in this example, the index would be 2, and the radicand would be 27. Over here to the right-hand side, we've got a coefficient of 12, which is the number in front. This number here is our index, which would be 3. So in this case, it's asking for the cube root, or what number times itself 3 times. And the radicand, the number underneath the radical symbol, would be the number 16. Now, before we get into simplifying square roots and cube roots, we need to talk about what it means to be a perfect square and a perfect cube. Perfect squares are the results of multiplying something by itself. So for example, 1 times 1, 2 times 2, 3 times 3, 4 times 4, 5 times 5, 6 times 6. Those are all examples of perfect squares. Now, that list can obviously continue on forever, but that's just sort of the beginning of it. Our variables can also be perfect squares. For example, x to the second, x to the fourth, x to the sixth, x to the eighth. Those are all examples of variables that are perfect squares. To be a perfect square as a variable, the exponent has to be even. So something like x to the 20th or x to the 100th, those are examples of variables that would be considered perfect squares. Also, perfect cubes, same idea, but a little bit different. Instead of a number multiplied by itself twice, it's a number multiplied by itself 3 times. So 1 times 1 times 1, which would be 1. 2 times 2 times 2, which would be 8. 3 times 3 times 3, which is 27. 4 times 4 times 4. 5 times 5 times 5. And again, obviously this list can continue on forever. It's just the beginning of it. It's the result of multiplying something by itself 3 times. Variables are also considered perfect cubes. Examples of those would be x to the 3rd, x to the 6th, x to the 9th, x to the 12th, x to the 15th. If you take a look at those exponents, they're all divisible by 3. So for a variable to be a perfect cube, the exponents have to be divisible by 3. Now, these steps that we have here are for simplifying radicals, simplifying square roots, cube roots, any kind of radical. First and foremost, we can leave no fractions underneath the radical. No perfect powers. That means we can't be able to simplify what's underneath there. No exponents in the radicand that are greater than the index. And really important, we're going to talk a lot more about this later, but we can't leave a radical in the bottom of a fraction. Our first example of simplifying a square root is the square root of 27. What I'm going to do for starters is make 2 empty square root symbols. I'm then going to think to myself, what is the largest perfect square that goes evenly into 27? And that's going to be 9. 9 times 3 gives me 27, so I'm now going to take the perfect square that I have on the left-hand side, and I'm going to cross it out and write its square root above. My answer in this case is going to be 3 square roots of 3. Same basic idea in my next example. I'm going to have 2 and then a square root of 40. So I'm going to make 2 empty radicals. If I look at my radicand, which is 40, I'm going to ask myself what's the largest perfect square that goes into 40, and that's going to be 4 multiplied by 10. Just like my last example, I'm going to take the square root of my perfect square by crossing it out and putting it on top. I then take what's on top and multiply it by what's in front, and that's going to give me a negative 4 multiplied by the square root of 10. Now, it might be very tempting to take the square root of that 4 because it is a perfect square, but there is no radical symbol around it, so this would be our simplified answer. Now, my next example, we now have a variable in there and a coefficient, so I'm going to do the same thing. I'm going to take 1/2, write it down, I'm going to make 2 empty square root symbols. Then I'm going to look at my radicand, starting with the 200. I'm going to ask myself the same question. What's the largest perfect square that goes into 200? That's going to be 100, and it's multiplied by 2. I'm then going to look at my variable. My variable is x to the 3rd. X to the 3rd is not a perfect square because the exponent is not even. So I'm then going to take that x to the 3rd and break it into 2 parts. One of my parts is going to be x squared, the other one is going to be x to the 1st. The reason I went with x squared is it's the largest even number that's less than 3. Once I have that all set up, I'm going to take the square root. The square root of 100 is 10. The square root of x to the 2nd is x. I then multiply that by my coefficient, and I'm going to end up with 5x times the square root of 2x. And again, that would be my answer. Next example, same idea. I'm going to go 5x, 2 empty square roots. I'm going to start with the 72. 72 is not a perfect square, so I'm going to think to myself, all right, well, what's the largest perfect square that goes into 72? If you think about it, hopefully we'll come up with the fact that 36 times 2 is 72. So 36 would be the largest perfect square. Then I'm going to look at my variables. I have an x and I have a y. X to the 11th is not a perfect square, so I'm going to do the same thing. I'm going to make x to the 10th on the left-hand side, and I'm going to go x to the 1st on the right-hand side. I'm now going to look at my y's. My y's are y to the 20th. Y to the 20th is a perfect square because the exponent is even. So for now, I'm going to keep that y to the 20th over here on the left-hand side underneath that radical symbol. Once I've separated my perfect squares from my non-perfect squares, now I can simplify. The square root of 36 is 6. The square root of x to the 10th is x to the 5th. The square root of y to the 20th is y to the 10th. Once I've simplified, I can now multiply that by my coefficient. If I take 6 times 5, that's 30. If I take x to the 5th and multiply it by x, that's going to be x to the 6th. And then that y to the 10th stays the same, and the square root of 2x to the 1st. You've probably noticed already, but when I take the square root of my variables, all I'm really doing, if they're even, is taking that exponent and dividing it by 2. All right, so my next example 5, I'm going to ask you guys to try on your own, and we'll go through it in class tomorrow. And again, pause the video, try the question, and then play the video again. Now, example number 6, we've shifted gears, now we're cube roots. Now, when I look at cube roots, I have to sort of change my mindset, and I'm not thinking about my list of perfect squares, I'm thinking about my list of perfect cubes. And our list of perfect cubes were 1 and 8, 27, 64, 125. That's our basic list of perfect cubes. I'm going to ask myself again, what's the largest number on that list that goes into 8? Well, obviously 8 is a perfect cube. So then I have to ask myself, what number times itself 3 times? And that, of course, is just going to be 2. Now, example 7, again, we're dealing with cube roots. So I'm going to separate this into 2 empty cube roots, just like I did with square roots. Now, 24 is not a perfect cube, but if you look at that list we just wrote down, the largest perfect cube that goes into 24 is going to be 8. 8 goes into it 3 times. Once I've figured out the largest perfect cube, just like before, I'm going to go ahead and take the cube root. The cube root of 8 is going to be 2. I'm going to end up with an answer of 2 cube roots of 3. Now, example number 8, you're going to notice that now we have a negative underneath our cube root symbol. Not something we should be too concerned about, because if you think about it, we're multiplying something by itself 3 times, and we can get a negative that way. So I'm going to take a look at the number 54, look at my list of perfect cubes. I'm going to come up with the fact that 27 is going to be the largest perfect cube, and 27 times 2. Now the question is where do we put the negative? I always put the negative with the perfect cube. When I simplify, it kind of takes care of itself. Now I look at my variables. I have x to the 6th. X to the 6th is a perfect cube because the exponent is divisible by 3. So the x to the 6th is going to go on the left-hand side. Now I look at my y's. It says y to the 8th. Well, y to the 8th is not a perfect cube because 8 is not divisible by 3. So now I have to take that and break it up into 2 pieces. I'm going to put a y on the left and a y on the right. Question now becomes what's the exponent? Now our rule for perfect cubes is the exponent has to be divisible by 3. The largest number that's divisible by 3, that's smaller than 8, is 6. So this becomes y to the 6th, and that becomes y to the 2nd. At this point, I'm going to go ahead and simplify. I'm going to simplify the cube root of negative 27, which is going to be negative 3. The cube root of x to the 6th, divide the exponent by 3, that becomes x squared. Take y to the 6th, take its cube root, again, divide that exponent by 3, that's going to be y squared. And then I'm going to go ahead and multiply it by a coefficient if I have one, but in this case I don't. So my answer is going to be negative 3, x to the 2nd, y squared, multiplied by the cube root of 2y to the 2nd. Again, perfect cubes are similar to perfect squares, but not exactly the same thing, so we have to be really careful. Now, the next couple of examples I think are pretty straightforward and easy, so I'm going to go through them pretty quickly. They're fractions. Now, when you take the square root of a fraction, you're going to take the square root of the number on the top and the square root of the number on the bottom. It just so happens that they're both perfect squares, so the square root of 25 is going to be 5. The square root of 36 is going to be 6. My next one is, again, same idea. It's going to be perfect cubes, again, as a fraction. So I'm going to make this, say, the cube root of 27 divided by the cube root of 8. Again, just so happens that the top and the bottom are both perfect cubes. The cube root of 27, of course, is 3. And the cube root of 8 is 2. So my answer to this one would be 3 over 2. All right, so what you guys are going to do right now is you're going to go to your next slide, and you're going to notice there are some practice questions that you're going to try. For homework, we'll pick up the pieces and see how we do tomorrow.